Okay. In the first place, we treat the one and then backprop algorithm should be built. Okay. In order to do that, we utilize this function and this function in terms of the what this update rule. Okay. And so, as always, we do import the numpy smp and import matplotlib.pyplot as plt in order to show the R results, and also import pandas as pd. Okay. So, first of all, generate the random data with noise, like this one. mp random seed must be assigned with the what? With this one. And num samples set assigned to 100. x1 is a vector mp linspace should be called 0 to up to 10, and num samples should be given here. And also x2 is assigned to the 5, and also x3 is assigned to the 3. Okay, we have the 100 samples in terms of what x1, x2 and x3 with the difference or the different range of this data. Okay, and so the noise mp random normal distribution can be used in here. Mean value 0 to std value and num samples is assigned, and y is a target vector 7 times x1 plus 12 times x2 plus 5 times x3 plus 5. This is a bias, and also we should assign to the noise. Okay. First of all, in order to stabilize the R training class, we need to normalize it. Okay, to input data. In terms of the what, to batch normalization, x1 minus mp mean x1 divided by mp std values of the x1. Okay, and so x2 and x3, x3, x2, x2, x3, x3. Okay, this is the batch normalization, guys. Okay, we also define the neural network structure. Okay, input size is assigned to 3 because we have the 3 inputs with a bias term, and hidden size is equals to, for example, we can assign to the 4, or we can change to this hidden size, but the output size must be equals to the what? Y. Okay, or y. So, in order to train this network, we need to firstly initialize weights and bias. Okay, mp random seed is assigned, for example, 1, and weights input hidden is generated as the what? The matrices. mp random rand function in terms of the what? The with the size of the input size and the hidden size. Okay, this is the W matrix, and biases hidden should be given with what? The mp zeros is assigned with the 0 and 1 hidden size. Okay. And also with the same architectures, the weights hidden to output can be defined with this one. Okay, and so this is the hidden size, this is the output size. Okay. And so output size and the bias output is assigned with this one. Okay, and this is the initialization of the weights and the biases in terms of what? The W and the V matrices. Okay, hidden to output and input to hidden. And hyperparameters can be defined with the learning rate is assigned to the what? 0.0001. For example, the max epoch is assigned to 1000 value in here, and also list for storing the mean, squared error, and the epoch values. Instead, MSE values is the list, and the epoch values is equals to list. Okay, and so for the training class, we need to build to the what to this case. First of all, we need to give the epoch in range of the max epoch up to what? Up to 1000th value. Okay, after that MSE should be equalized to the 0, because at the every epoch we need to reset the mean squared error value. So and so for I in range of num samples should be given here. In this case, we have the 100 values for a given what the y and which pair of the x1, x2, and x3. Okay, and so firstly, we need to give the forward pass in order to calculate the y or the output values of these values. Okay, input layer is assigned to MP array. This must be collected with the what? With this list structure x1 I, okay, and x1 2 and x1 3. Okay, and hidden input should be calculated with what? The MP dot input layer and weight input to hidden plus biases hidden. Okay, after that hidden output should be defined with the sigmoid function 1 divided by 1 plus MP x function should be called with what? Minus hidden input. Okay, and so final input should be calculated with the what? The MP dot operator hidden output and weight hidden output plus biases output. Okay, and so the final output is assigned to the final input. This is the forward pass, and so this final output is assigned to y. Okay, after that we need to calculate mean squared error. So error is equals to what? Y I value minus final output. Okay, and total MSE should be added to the what? Error square. Okay, and so what is the backpropagation? How we can update the calculations of these terms? First of all, the output is the derivative of the output minus 2 times error. Okay, this is called the what to this one, but we don't have the 1 divided by 2 terms in here, and so this 2 is going to be in here, and so we have minus 2 times error, and d hidden is assigned to d output times dot weights hidden output dot t times hidden output times 1 hidden output. Okay, and after that update weights and biases. It's given here. Weights hidden output minus equal to the what? To the learning rate times hidden output t dot, and d output must be given in here. This is the multiplication of the what? Transform of the this vector. Okay, and also biases output must be updated with the what? Minus equals to the what? Learning rate times d output. Okay, and weight input hidden minus equal to the what? Learning rate, right? Times input layer t dot d hidden. Okay, and biases hidden should be assigned with the what? The learning rate times d hidden. So after that, for the whole values which is threaded in the what? In the up to the num samples, we need to calculate the mean squared error in here. for a new samples, and so MSE values should be appended into the MSE, and also epoch values must be appended with the epoch. Okay, if epoch percentage 100, which is equals to 0, and so at each 100 samples epoch should be assigned with the epoch value, and MSE mean score error is assigned to MSE. Okay, this is a training class. So how we can predict or test our algorithm? Depth predict is a function for a given x1, x2, and x3 in here, and so input data should be defined in here, MP array, just like this one, and x1 I or x1 and x2 and x3, right? But it's the double array. Okay. And so hidden input should be assigned MP dot input data weights input hidden plus biases hidden. This is the hyperplane noise, right? And after that, the hidden output is equals to 1 divided by 1 plus MP exponential terms of the minus hidden output. This is the sigmoid function, right? And so final input is equals to MP dot hidden output weights hidden output, right, plus biases output. This is the second layer hyperplane. Okay. So the final output is equals to the final input, and return to the final output 0 and 0. Okay, because it's the double array. And so after that, we need to plot the figure just like this one. Plot y color blue, and the label should be assigned to the real target. Okay, and the line style, which is equals to the dashed. And after that, predicted values can be calculated with the with predict x1, x2, and x3 should be given in here for the x1, x2, and x3 in zip x1, x2, and x3. Okay, and PLT right now, this is the predicted values, this is the color red, this is the neural network prediction and prediction. Okay, PLT X label, this is the sample. PLT Y label, this is the value, and PLT title, which is equal to real and predicted target. PLT legend and PLT show must be given in here. Okay, and after that also save data, maybe data PD data frame, which is in terms of the x1 is key, x1, x2, and x2, and x3, and x3, and y, and y. Okay, and data to Excel should be called, for example, nn data dot xlsx, and index should be assigned to the false. Okay. So this is the training class with the basis of these terms, just like this one. V and W is updated based on these terms. and so we can train our neural network. And so if I run this code, see the mean square error, sorry, local sensor reference defined, and so line 86 predicted value, this one, NPX hidden out. I'm sorry, hidden input should be assigned in here. Okay. And so the mean square root is going to the what? Going to the 0, but at the 1000 epochs it closes to the what? To this one. This blue line is the real target, but the NM prediction is closing to the what? To the this one. Okay. And so how we can optimize this algorithm? First of all, we can change the learning rate in here, just like this one. But the learning rate is increased, and so our data is fluctuated in here because we cannot reach the every point of these terms in here. Okay. And so if this is not work, and so I'm rerun this code, and so this is more perfect, but I should increase the what? The num epoch number in here up to what? 2000's value. Okay. See, this is the more straight right now, right? Or we can assign to 5000's value, and so we can more obtain the more predicted or the true values of the what? This date, because it's closing to what? 0, right? Or we can change the hidden size number. For example, if I choose the 6 and so see right now it's going to what? To the 3, but my network possessed what? The 6 hidden neuron right now. Okay. I increase the performance, the accuracy rate of these terms by adding the new neurons, just like this one. But if I add the 10, and so this is going to the what? Right now, Q, and so this is the more precise results for a given the predicted and target values of these terms. Okay, and so we need to optimize our neural network based on these combinations, and so we need to train or design the proper hyperparameters based on the what? Based on this case. For example, if I choose the 20 values in here, maybe see in the 20 we can reach to the what? Maybe the 2 value, but maybe this is the most perfect line for the what? For the algorithms. Okay, the real and predicted target is closing much more than before right now. Okay, or we can assign the what? The new learning rate in here, and so our results may be changed. See, at the instant value reaching the 3 but not the 2, maybe we should increase the what? The 10,000s epoch in here, just like this one. But our network, the MSE error, is stuck in the 3.45 because it's a straight line right now, right? Maybe we cannot model further. Okay. This is the what? The first NM backpropagation algorithm with the Baremetal Coding. Okay. So we need to continue with the what? We are 2 and then Backpropagation Pytorch example. Okay. First of all, in order to do that, so we need to use these definitions with the same before. These are the data set. Okay. And so we need to import right now torch because we need to import it. We have to use its function and import torch nn as nn and import torch optim as optim and import numpy as mp. Import to visualize the whole dataset matplotlib.pyplot as plt and import pandas as pd. Okay. In order to generate the random dataset, we need to add also the manual seed for the torch. For example, the 1. Okay. And after that, x1, x2, and x3. This is a training dataset in here, just like this one, but in this case, we need to combine the whole features and convert to torch tensors, because we need to utilize the torch. X is MP column stack with the what, with the tuple value x1, x2, and x3. Okay, and x tensor should be assigned with what, with the torch tensor should be created in here, just like this one, x, and d type should be given in here, torch float 32. Okay. And also y tensor should be assigned with the what, with the 1. Okay. But this is assigned real -1 and 1. Just remember the previous lesson. Okay. In order to define the neural network in the torch, we need to build the what, the class simple net. It is inherited with the nn module. Okay, because the nn is coming from the what, the torch nn, and so the whole function which is given in the module is passed into the what, input into the simple net right now. Okay, and so that init function should be assigned in here, and so self input size, hidden size, and output size should be given as a constructor parameters in here. Okay, and so for the super simple net, and self should be given here, and the constructor should be called right now. Okay, because this constructor calls the nn module constructor. Okay, and so self fc1, the fully connected layer, which is the what, which input the hidden layer, can be created with what, the nn linear neuron with the parameters of the input size and the hidden size. Okay, this is the input to hidden. Okay, and after that, self sigmoid function is defined nn sigmoid. Okay, this is the activation function. And also self fc2 is assigned to nn linear is with what, the hidden size and the output size. Okay, this is the hidden to output. Okay. And after that, in order to forward the whole terms, that forward function must be rewritten in here, just like this one. X is an input, self fc1 should be passed x, and x is recreated again the sigmoid function with the x. This x processed and generated with the new x. The new x is fed into the sigmoid, and sigmoid generated the new x. And also x self fc2 x, and return the total x in here, just like this one. Okay. After that, the algorithm can be built with this one. First of all, the input size is assigned to 3 because we have the 3 inputs, and the hidden size should be assigned for 4 or 5 or 10. We don't. Output size is the 1, and so the model can be created with the simple net with the what, input size, hidden size, and the output size, because the R constructor should be taken these parameters. Okay. And after that, we also build the loss function and the optimizer, which must be done in here. The criterion is assigned with the what, the nn and sl loss. This is a default function to what? To calculate the mean squared error loss, which is written in the what? In the torch or the PyTorch. And so the learning rate is assigned with the what? 0.01. Okay? And so the optimizer should be also updating here optim stochastic gradient descent model parameters should be given just like before in the previous lesson. The learning rate should be updated. And so max epoch should be assigned 1000 and MSE values is empty list. Okay? So for the training for epoch in range of max epoch. Okay, model should be trained, and so we initialize it. And optimizers should be assigned to 0 grad. Remove all the gradient values. Forward pass should be done with the what? With the outputs of the what? The model should be passed to X tensor. Okay, and after that, compute the loss. Loss equals to what? The criterion, the outputs, and Y tensor. Okay, this is the mean square. And after that, backward pass should be given here. We need to compute the gradient of the loss with respect to the model. Okay, in here we compute the loss, and so the loss backward is calculated gradient of the R losses, and after that perform a single optimization step, parameter update, which means that we update the whole the coefficient W and V optimizer step. Okay. And also MSE values should be appended with the what? With the loss and item. This is the general error for a given data. And so if epoch percentage 100 is equal to 0, and then print f epoch should be show the epoch and MSE equals loss item. Okay, this is the training class of the what? The R algorithm. Okay, and so what about the test? Testing class. In order to test, the def predict should be given with the x1, x2, and x3. Okay, and so model evaluation mode is open, and so with torch no grad calculation should be opened in here. Input data must be assigned with what? The torch tensor, which is equal to what? X1, x2, and x3. Okay, and also the type should be set with what? The torch float 32. Okay, after that, the prediction at each case should be obtained the model input data, just like this one, and so we need to return the prediction item because it's our results. Okay, and after that generate the predictions. Predicted value just like before is assigned with what? To predict x1, x2, and x3 for x1, x2, and x3. This is a comprehension, guys. Just remember the Python lesson, or just watch my YouTube video list about it. And after that, we need to copy all this term in order to visualize our code. Okay, y and predicted values should be removed in here because we calculate it in here just like this one, and so we can show all the terms in here. And so if I run this code and see the MSE is up to what? Up to 900 is going to what? 8 value in here. And so the R neural network is set to the correct values or closing to what? The real one in here. Even if it has possessed a noise value. For example, if we have the 10,000s is assigned in here, just like this one. See, this is going to the what? Much closer to the what? The real. Okay? What about the hidden size? If I increase the hidden size or hidden neuron is up to the 10. See, it's more straight line, or its performance is passing to the what? To the before one. Okay? This is perfect. Or we can assign to what the many values in here. See, it's going to the what? The straight line, because our data set is coming from the 7, 12, 5 and bias term of the 5. Okay? This is how we can model or build this data based on the what? Based on this test. Okay? And so, what about the Baremetal Coding? By using the Pytorch implementation, because in this case we utilize the loss backward loss function and the out of the model in here. This is simple stuff. But if I choose the what? The increase of the complexity or the Baremetal Coding of this one, just like this one. This is the word 3 and then backprop, Pytorch and Baremetal. So in order to build this, first of all, we don't need to utilize the opt-in function in here, and also we need to cap these tensors in here and a simple one. And the rest of them should be written in here. But just remember the previous lessons. We create the X tensor and Y tensor as a training data. But we can also create a train and test sequence based on the what? Based on the R algorithm, randomization, or the what? Cross validation technique. And we will use 80% of the data for training and the rest of them for testing. Okay? And so how we can do that? Num train data is assigned with what? The int num samples times 0.8. Okay? So if we have the 10 or the num samples is equals to 100 or 1000 data, and so 800 data is utilized for what? For the training. Okay? So indices can be built with what? The torch rand permutation command. Num samples, it shuffles all the num samples based on the permutation. Okay? And so the train index can be built with what? With the indices 0 to num train, and test indices is the indices num train and the end of the data. Okay, this is the 0 to num train to the end. Okay, and so X train can be built with what? The X tensor with the what? With the trains. Okay, and so this is the Y train, and so this is the train this. Okay, and so this is the Y tensor, this is the Y tensor, this is the X test, and this is also test. Okay, X tensor, but this is the test in this. Okay, and so we have 80% of data for training the other 20% is for training. Okay. The neural network is the same in here, and after that we need to define the input size 3, hidden size is 4, and the output size is equal to 1. Okay, and after that the model should be built with the what, with the simple net input size, okay, and the hidden size and output size. Okay. So for this case we need to build the hyperparameters for manual Adam optimizers, adaptive moment estimation. It's different with what stochastic gradient descent or the gradient descent algorithm, but we need to add the adaptive learning rate in here. Okay, so the learning rate is equal to 1e minus 3 and beta 1 0.5. This is the first moment parameter, beta 2 0.0999. This is the second. Epsilon is equal to 1e minus 8. I will talk about it. And so max epoch value is equals to the what? The 5000 in here. Okay. For the adaptive learning rate, we need to give limits. LR. For example, mean LR is equal to 1e minus 8, and max LR is 10. If we have low update, and so the LR is increased. If we going to the what, the small update, and so the LR must be smaller in order to stabilize our training class. Okay. So after that, we need to also build the bed size in here. What's the bed size? Okay, I will talk about it in here. First of all, the initialized state dictionaries for first and second moment estimates, which is coefficients of the neural network, param states. Okay, this dictionary value. So for param in model parameters, this is called what model parameters is the what, the W and the V matrices, and so param is the each of these coefficients, and so the param states is assigned with the param is equal to what is also dictionary, and so the M is equal to the what torch 0 slot. Param is the initialization of the coefficients, and V is also torch 0 slide param. Okay. We built this because we need to reach the whole the coefficients of the neural network. In normal case, you don't need to do that, but I will show the what is the Adam optimizer, which is useful or the which has the great advantage on the stochastic gradient or the gradient descent algorithm in order to train your neural network. Okay. MSE values is empty list and preloss is float. Infinite value is assigned in here. In the first place, the global stack is equal to 0, and train samples is assigned x train dot shape is 0. This is the first dimension parameter or the number of the this term. This is just like of the what, the length of the x train vector. Okay, it's returned. After that, for epoch in range max epoch. Okay. Model train should be opened in here, and the epoch loss is equal to 0.0. Okay. First of all, we need to shuffle all the training data at the beginning in order to stabilize our training class. Okay. Each. So the permutation is assigned with what, a torch runs perm train samples. Okay. So how we can apply the batch size in the neural network? We can use the whole data in order to what? In order to calculate the total loss function. But this is used, maybe in some cases this is insufficient, because if we have, for example, 5 billion training data, and so in order to update the neural network coefficients, we should calculate the billion times of this loss function and collect the whole terms. After that, we need to define the updated parameters. But instead of using this, we can define the mini batch size in here. For example, the 1000 data, which means that at each 1000 data for this training data, we can calculate the mean squared error, and we updated the neural network coefficients, and so it is fastened to the what? To the training class. Okay. This is the definition of the what? Batch size. And so for I in range of 0 to train samples, but at each batch size. See, in this range we are going to do what? The train samples, but at each batch size. Okay. And so the indices is updated to permutation of the what? I to I plus batch size. We obtain the whole the terms in here. And so X batch should be calculated with what? X train. Okay. And so indices should be given in here. And also Y batch is obtained Y train. Okay. And after that, model 0 grad should be assigned in here. And so outputs should be calculated with the model X batch. For example, if I choose this one is the 16, and so 16 values of the train sample is done, or is calculated to what? To compute the mean square error and the weight update rule. Okay, but we have 1000 data in here. See, and so at each batch we updated the coefficient, and so it passes. It increases the what? The stability of the training of the our neural network. Okay, but in some cases, the loss and an MSE loss is assigned with the what? With the outputs and Y batch, right? And so loss backward should be called in here just like this one. And so the global step should be updated in here with the 1. Okay. And so we need to update right now the coefficients based on these parameters. We obtain the loss, we obtain the gradient values of this term, and so manual add-on parameters update must be done, but for the current mini batch or batch size. Okay, with torch, no grad should be updated in here because we calculated instead of Pytorch. And so for param in model parameters, okay, if param grad is none, or we don't have any gradient in here, and so we need to continue. But if this is not the case, and so the grad is obtained from the what? The param grad data. So the gradient is obtained, and so state is obtained from the what? The param states from the what? The param. Okay. And after that, update biased first moment estimate in here, which means that state m is equals to the beta 1 state m plus 1 minus beta 1 times grad. See that? If you choose the beta 1 is greater than the 0.5, and so the instant moment of the state is updated in here, but the grad is not instantly transferred to the state m. which means that if we want to update the gradient instantly, we need to select the beta 1 is here is small. Okay? Otherwise, we cannot do it. And so, update biased second moment estimate. And so, state V is assigned beta 2 times state V, right? Plus 1 minus beta 2, but in this case, this is the second moment, grad square term in here. Okay? After that, we need to compute bias corrected estimates using global step. This is complex, but if you analyze the code, you can see that this is easy. M and 1 minus beta 1 global step. For every case, we need to what the overturn, apply the overturn of the global step, which means that the m hat is greater than to the what, or m hat is smaller than to the what at every global step. Okay, this is the moment. Okay, and so we have is also assigned with the what with this one, but in this case we, and so this is the beta 2. Okay. And after all, update the parameters using the current learning rate, guys. Okay. In order to do that, param data is the coefficients of the matrix param data minus learning rate should be given in here, but m hat divided by v hat square root of this term plus epsilon. If it is taken, the v hat may be coming to the 0, and so this epsilon stabilizes the r division operator in here. This is just kind of the batch normalization update, but it's the moment update in here. So after that, we need to what epoch loss should be calculated in here. Plus equal loss item each case times len indices, because in the mini batch size we do not compute the every data, just only the batch size. Okay, and after that, if this is the case, and so the total epoch loss is obtained division equal to the what the train samples in here. And so total MSE values append should be assigned with the what? With the epoch loss. Okay? So, after that, how can assign the adaptive learning rate? Based on loss. If epoch 0 is greater than the 0, and so if epoch loss is smaller than previous loss, which means that this loss, for example, epoch loss 5 and previous loss 4, which means that the learning rate must be assigned what the minimum values of the max LR and the learning rate times 1.05, which means that we need to increase the learning rate. Okay, because the epoch loss is smaller than the previous one. Else, in this case, we need to smaller than this one, the maximum values of these terms, but instead of what, the mean LR and 0.7. Okay, because in this case the previous loss, for example, 5, and this is the 4, and so we need to what, we need to increase the R learning rate in order to what, in order to obtain the stable performance in the training class. Okay, but otherwise we need to smaller than this one. So After that, the previous loss should be assigned to the epoch loss, because in the first place the epoch loss is recalculating here. The previous loss is the what is the previous. Okay. So if epoch percentage 100 is equals to 0, print f epoch and train MSE is equals to the what epoch loss dot for f, and learning rate is equals to what learning rate dot 6f. Okay. After that, we need to evaluate the R result evaluation on test data. Okay. Model eval should be set with torch no grad should be assigned in here. Test outputs we assign the model x test. Okay, and test loss can be calculated with what nn MSE loss with the what parameters of the test outputs and the y test is the real. And after that we need to print what f test MSE is equal to the what test loss item and dot for f. Okay. So this is a test result, and so after that we need to complete the total prediction on the whole data set. Okay, with torch so should be copied in here just like this one, but this is the full outputs, and so this is assigned to extensor. Extensor process the whole data, and the full output is given in here, and after that the full outputs ME should be given with what the full outputs numpy is the conversion method. Okay, and that flat. Okay, and YMP also should be converted with what with the tensor numpy. This is the conversion of the numpy, and the flatten should be assigned in here. Okay, so in the last place PLT figure, PLT plot should be running YMP, and so the label is assigned with what with the real target. Okay, line style is assigned to dashed, and the color is blue. Okay, and also the full output MP should be given in here, and this is the prediction. Okay, and the color is red. The difference. So PLT X label, sample index, and PLT Y label is assigned to the value, and PLT title real and predicted data on all the data set, and PLT legend and PLT show must be given in here. And so if I run this code, finally see the epoch is going to the what is going to the smaller and smaller this one, but the learning rate is instantly changed in here, just like this one. The learning rate is coming from 10. I'm sorry, this must be 10. Okay, or not. See, the learning rate is instantly increased, and after that decrease in order to stabilize the R training class, just like this one. Okay, and so this 5, and after that the R training class is recalculated based on this moment and the explanation of this place. Okay, but for this case, the batch size is 16, which means that at each 16 sample, its gradient is updated in here. And so, how come we optimize the batch size in here? See that this is equal to what? 5.2020. But in the last case, we have the greater or smaller values for the train. And so, max epoch is decreased to the what? 1000. And so, what about this? If I select the 2056 in here, just see the results right now. See, the train MS is going to do what? The 90 in here. But in this case, train MS is 5.2020. Okay? And so, in the last case, the batch size 16 is produce the better results, right? And so, we can say that it's more appropriate to what? To train our networks in here. See, this is the what? This is the 5.58. It's better than before. And so, maybe, for example, if I choose the 32 in here, see, it's going to the what? It's closing to 5.72. Okay? Okay, and so what about this one? If I choose the 1000th value, which means that we don't use the what? Our numbers in here. We don't use the mini batch because we have the 1000 data, but we set the whole the max epoch or whole the batch size the 1024, which means that we utilize the whole the data at 1 second, just like this one. Okay, and so how we can update our batch size? For example, if I choose the 8 in here, see, in the 8 we update the whole the coefficients at the 8 batch size. See, our training class is closing to at the 4.51, which is better than before, right? See, we need to optimize our neural network based on these informations. Okay, and so we need to optimize the whole the hyperparameter based on this information. For example, if I choose the mean LR function up to what? The 1e minus 10. See, right now it's going to the what? 4.51. There's nothing changed in here, but this is the 8 and this is the 16 or 16. Okay, what about this one? If the beta is 0.1 is assigned to 0.1 for this data set, what's the effect of the distance right now? In this case, we are closing to the what of 5.36, right? See, if I choose the 0.9, the gradient effect is more than before. See, the performance is degraded up to what? 42. Okay, and so what about this? If I choose the using the whole the batch or the whole the dataset, but if I choose the beta is 0.9, what's the result? See, it's going to what? 12 values in here, just like this one, but we need to increase the what? First of all, if we set the 0.1 in here, just like this one, see, in the 0.1 we are closing to what? The slow or degraded performance, which means that if I choose this dataset or the parameters in here, and so just see that if we choose the 0.99, and so we cannot close the real result in here, which means that we need to optimize our neural network. Based on these parameters, we need to apply the optimized performance on this dataset. We need to try the whole beta and beta 2 value, or the max epoch, or the max LR, or the mean LR values in order to what? In order to train our neural network. This is called hyperparameter optimization. This is important. All the great companies has these hyper optimization rules in order to train their networks, just like the GPT-4 or GPT-03 or something like that. Okay, this is the professional of what the training of the neural network based on this information. Okay, so